Every single time you click your mouse, type a key, or even just move your cursor across the screen, there's a storm of activity happening inside your computer. We're talking billions of operations every single second. So what's stopping all of that from just turning into a jumbled, chaotic mess? What's the secret that keeps our digital world in perfect working order?
Well, let's think about a real-world problem to wrap our heads around this. Imagine you and a friend share a bank account, and it's got exactly $100 in it. Now picture this, at the exact same millisecond, you both go to different ATMs and try to withdraw $10. The balance should be $80, right? Simple math. But what if the computer messes up and the final balance ends up being $90? Where did that other $10 go? It just vanished? It fell into a kind of digital black hole, a place we call a race condition.
So here's exactly how that disaster happens, step by step. First, your ATM, let's call it process A, reads the balance. It sees $100. At almost the same instant, your friend's ATM, process B, also reads the balance. It also sees $100. Now your machine does the math. 100 minus 10 is 90. But wait, before I can save that new balance, your friend's machine also does its math, and it also calculates a new balance of 90. Then, your machine writes $90 to the account. And just a heartbeat later, your friend's machine overwrites that 90 with the exact same $90. You both got your cash, but the bank just lost $10.
This very problem, this challenge of preventing digital chaos when multiple things are happening at once, is at the core of operating system design. And that is exactly what we're here to talk about. Today, we will deeply understand Chapter 5, Process Synchronization. We're going to pull back the curtain and see the powerful tools and elegant rules that operating systems use to make sure our digital world runs like a perfectly oiled machine. So here's our game plan for today. We're going to start by really defining what this race to corrupt data is all about. Then we'll formalize it into something called the critical section problem. From there, we'll explore the solutions, from the raw hardware all the way up to fancy software tools like locks and semaphores. We'll even use these tools to solve some classic computer science puzzles. And finally, we'll see how it all comes together in the real world with things like monitors. All right, let's dive in. The race to corrupt data. That bank account example? It's a classic case of what's known in computer science as the producer-consumer problem. You can think of one process as producing data, like depositing money, and another consuming it, like withdrawing money. The problem starts when they both try to touch that same shared piece of data, that account balance, at the same time. That's when you get a digital train wreck.
And this leads us to our first official definition, the race condition. So what is it, really? It's any situation where the final result depends entirely on the unpredictable, split-second timing of which process gets there first. In our example, the account ended up with $90 simply because of one specific unlucky sequence of events. If the timing had been just a little different, the balance might have been correct. This is like digital Russian roulette, and for an operating system that needs to be reliable, that's an absolute nightmare.
So this brings us to the absolute heart of the matter. The critical section problem. This is the big question. How do we design a protocol, a set of ironclad rules that allows different processes to cooperate and share data without tripping over each other and corrupting everything? How do we build a sort of digital fortress around our important data, a special zone where only one process is allowed to be at any given time?
The solution begins by thinking about the structure of our code. That part of the code that actually touches the shared data, like updating the bank balance, we call that the critical section. Now, to protect it, we have to wrap it in two other parts, an entry section and an exit section. The entry section is like a bouncer at a very exclusive club. Its job is to check who's trying to get in and make sure only one process gets past the velvet rope at a time. The exit section is that same bouncer, making sure you leave properly and signaling to the next person in line that it's now their turn.
Now, here's what's really cool. Any good solution, any good bouncer, has to follow three very strict rules. First, mutual exclusion. This is the obvious one. Only one process is allowed in the club, in the critical section, at a time. Second, progress. If the club is empty and there's a line of people waiting outside, the bouncer can't just decide to take a coffee break. Someone has to be allowed to enter. Things must move forward. And third, bounded waiting. This means you can't be stuck in line forever. There has to be a limit on how many other people get to go in ahead of you after you've made your request. No cutting and no starving.
So how do we actually build this bouncer? How do we enforce these rules? Let's take a look at some of the solutions. starting with a really clever, but nowadays mostly historical, software approach. Then, we'll get into the powerful hardware features that all modern computers rely on.
Okay, check this out. This is Peterson's solution, and it's a brilliant thought experiment for just 2 processes. Think of it like an incredibly polite dance. Each process, let's say process I, starts by raising its flag, saying, hey, I'd like to enter the critical section. But then it does something really clever. It immediately sets the turn variable to the other process, J. It's basically saying, I want to go in, but you know what? You can go first. Then it enters this while loop. It waits only if the other process also has its flag up and it's their designated turn. It's this beautiful little piece of logic that guarantees only one can get through. It's a real testament to the ingenuity of early computer scientists, even if modern computer architectures mean it's not guaranteed to work anymore.
In the real world, all modern synchronization is built on top of special instructions provided by the hardware itself. The magic word here is atomically. An atomic operation is something that is guaranteed by the CPU to be absolutely indivisible. It happens all at once with zero chance of being interrupted partway through. Instructions like test and set or compare and swap let us do things like check a lock and then flip it from unlocked to locked in a single unstoppable step. These are the fundamental, rock-solid building blocks for every other tool we're about to discuss.
Now, using that raw hardware power, operating systems give us, the programmers, a much friendlier set of tools to work with. We don't have to fiddle around with these atomic instructions directly. Thank goodness. Instead, we get to use higher-level concepts, and the most common ones are mutex locks and semaphores.
So the simplest tool in the box is the mutex lock. And mutex is just short for a mutual exclusion, which we already talked about. The best way to think about a mutex is that it's like a key to a single-person bathroom. Before your process can enter the bathroom, the critical section, it has to acquire the key. If someone else already has the key, you just have to wait. Once you're done, you release the key and the next person waiting in line can grab it. It's simple, it's effective, and it is the absolute workhorse of process synchronization.
Now, what does it actually mean for a process to wait? Well, there are 2 ways it can happen. The inefficient, kind of rude way is called busy waiting or a spin lock. The process literally sits in a tight loop hammering the CPU, asking over and over and over again, is the lock free yet? Is it free yet? How about now? It's just burning precious CPU cycles doing nothing useful. The much smarter way is called blocking. Here, the process basically tells the operating system, hey, I'm waiting for this lock. Just put me to sleep for a while and wake me up when it's available. This frees up the CPU to go do other useful work instead of listening to a process complain.
So if a mutex is a single key, a semaphore is a step up. It's not just a key, it's a counter. Imagine a bike sharing station that has 5 bikes available. The semaphore's value would start at 5. Every time someone wants a bike, they perform a wait operation, which decreases the count to 4, then 3, and so on. If the count ever hits 0, the next person who shows up has to wait. When someone returns a bike, they perform a signal operation, which increments the count and lets one of the waiting people know a bike is now free. So you can see that a mutex lock is really just a special kind of semaphore where the count is always just 1.
All right, so now we have our toolkit. We've got mutexes and we've got semaphores. It's time to put them to the test. We're going to use them to solve a few classic synchronization problems. You can think of these as the standard puzzles or benchmark challenges that any new synchronization tool has to be able to solve correctly.
Let's go back to our producer-consumer problem, which we can now properly call the bounded buffer problem. Here's how the producer's code works. First, it performs a wait on a semaphore called empty. This is basically asking, is there an empty slot in the buffer for me to put my stuff? If the answer is no, it just waits patiently. Once it gets the green light, it calls wait on a mutex. This is to make sure it has exclusive access while it's actually modifying the buffer. It adds its item, releases the mutex, and then, as its final step, it performs a signal on another semaphore called full to announce, hey everyone, there's one more item available.
And on the flip side, the consumer's logic is the perfect mirror image. It starts by doing a wait on the full semaphore. It's asking, is there at least one item in the buffer for me to take? If the buffer is empty, it waits. Once an item is available, it acquires that same mutex lock for exclusive access, removes the item, releases the lock, and finally, it does a signal on the empty semaphore announcing, hey, I just freed up a spot. It's this beautiful, symmetrical dance of semaphores that ensures the producer and consumer never get in each other's way.
Here's another super common scenario, something that's crucial for things like databases. Imagine a bunch of people are just browsing a website. They're all readers. It's totally fine for all of them to look at the same data at the same time. No problem. But When an administrator needs to update the site, they're a writer, they need exclusive access. No one else can be looking while they're making changes. So the solution lets any number of readers in at once. But as soon as a writer shows up, it puts up a stop sign for any new readers trying to get in, waits for the current readers to finish up, and then the writer gets the whole place to themselves.
And now for a famous one. This is a problem that perfectly illustrates the danger of something called deadlock. The setup is this. 5 philosophers are sitting around a circular table. There's one chopstick between each of them. To eat, a philosopher needs to pick up both the chopstick on their left and the one on their right. Now, what happens if every single philosopher picks up their left chopstick at the exact same moment? Think about it. Everyone is now holding one chopstick, and they're all waiting for the chopstick on their right, which is being held by their neighbor who is also waiting. No one can eat. No one will ever release their chopstick. They are all stuck forever. They will all starve. That is a deadlock. It's a critical lesson. A series of perfectly logical individual steps can combine to create a catastrophic, total system failure.
As you can probably guess from that philosopher's problem, using low-level tools like semaphores can be really tricky. One wrong wait or a misplaced signal, and you've got a deadlock or a race condition on your hands. These classic problems really highlighted just how easy it is for programmers to make mistakes, and that's what led to the development of safer, higher-level synchronization tools.
So it's all about choosing the right tool for the job. Mutex locks are great for simple, exclusive access to one thing. Semaphores are for managing a pool of several resources. But the real evolution here is the monitor. A monitor is like a super smart toolbox. It doesn't just give you the tools, it has safety features built right in. A monitor bundles the shared data and all the code that can access it together into one package, and it automatically ensures that only one process can be using that package at a time. It makes it basically impossible for a programmer to make common mistakes like forgetting to acquire a lock or releasing a lock they don't hold.
So, there we have it. We have just gone on a deep dive, all the way from the potential chaos of a simple race condition down to the atomic instructions in the hardware and all the way back up to powerful tools like locks, semaphores, and safe high-level monitors. We have figured out how to make all of our processes cooperate safely and wait for their turn politely. But that brings up a brand new question, doesn't it? When you have multiple processes all ready and waiting to run, how does the operating system decide which one actually gets the CPU next? And that, my friends, is the topic for our next explainer, CPU scheduling.